Taylor Barton and Mariano Oliveira in the back, waving his hand, are the team from Boston. And no, I didn't bring them along with me, which if you had heard the Naked Scientist the other day, that may have been a question that was asked. They're from Seascope, which is I guess a company that you two have founded. And
we're not even really a company. It's a name for our hobby at this point.
Okay.
Yeah.
And they're doing the sailboats as a hobby, but they've come a long way. And both of their papers are really interesting. Taylor's going to talk about really a motionless wind detection device, which means, in particular, Matt would be happy with this because that seems to be what breaks the most on our boat. And then after Taylor, Mariano will be talking about. Shoot, I just looked it up. Hold on. Yes, the single board computer for autonomous sailboat control. All right. And you guys can blend together the amount of time you need on each.
Okay, sure. So, so we're just sort of doing this as a hobby in addition to our regular job. So this year we didn't get quite as much time to test on the water as we would have liked. But the two papers sort of talk about some more kind of lab-based stuff that we've been doing. In particular, this one that I'm talking about is really even a side project to our hobby, which is just a sort of optional wind sensor that we kind of thought would be a neat adaptation of a device that is found usually in a CMOS implementation as an integrated sensor. So if you look at, if we ever get our boats running this week, you won't see this on it. It's not at that stage yet. We're currently just using a wind vane. But the idea is that we have, I think all of us this year are using wind sensors, wind direction measurement for the control. I think last year there was a group that was looking at avoiding that problem. The reason people want to avoid this problem is that they fail a lot. They're not very reliable. And that's mostly true of the sort of vane type wind sensors where you have a moving part. And anytime you have a moving part, that's going to be the thing that breaks. So there are actually a few different approaches that you can take with wind measurement. And they trade off size, cost, this mechanical robustness, whether it has moving parts or not. They trade off sort of a software complexity, how much calibration is required, as opposed to just getting a simple measurement of voltage proportional to wind or what have you. And accuracy is another one. So I've sort of summarized 4 kinds of approaches that you can do. The most common one, or the simplest one, is to just use a potentiometer and a vane. And this is cheap. It's a really bad idea mechanically. That's what we do because we're doing this sort of competition, around buoys. Certainly nobody going across the ocean would want to do this in terms of like the wiper of the potentiometer. But it's cheap, it's small, it's relatively lightweight, and it's very simple in terms of calibration. An improvement on that is to use the magnetic encoder that Alex's boats use, and I think a lot of people here might also use this, which gives you contactless. You now have real bearings instead of a potentiometer, which increases the mechanical complexity in terms of constructing this, somewhat over just the potentiometer, but the cost is incrementally higher potentiometer. And again, it's a very simple output signal from that chip. The other kind of end of the spectrum is a very expensive ultrasonic wind measurement. This is ideal for, like, mechanically speaking. It's another option to not have moving parts. For us, the cost and also the size of sort of commercial models is prohibitive to our little boat. And if you were going to make one, it would be complex to do yourself, which would be potentially another option. But the one that we decided to explore is this temperature-based 2D-Array sensor that I'll talk about. And It's cheap, it doesn't have any moving parts, it's very small, I brought it with me, I'll pass it around. And like the ultrasonic, it's temperature dependent and humidity probably dependent. If you put a drop of water on it, its properties change more so than the potentiometer-based version. So it's, we've basically traded off mechanical complexity for software complexity. And it's, all of these four options basically represent trade-offs in this space. So it's not necessarily, the best option depends on so many factors. We're not making any claims that we should all switch over to the thermal one. You'll see also that the bandwidth is an issue. But we wanted to explore this just as an alternative to our current, really basic potentiometer method. So let me talk a little bit about just the operating principle, how this thing works. Fortunately, sort of cut off a little on the bottom. These are just all grounded nodes. This sketch is sort of a circuit sketch of the layout of the device. We have a central resistor that we're just putting power into this resistor to heat it up. So we're just providing a heater here. And then the outer devices are actually thermistors, so their resistance values change depending on their temperature. So if we have, say, a wind from starboard to port, along this vector, what happens is the heat gets carried from the heater to these, and asymmetrically heats resistors on either side of the central device. And by connecting the thermistors in a sort of a bridge configuration, we get a differential voltage corresponding to sort of the fore-aft differential heating, and then another differential voltage corresponding to starboard port heating. And from those two quadrature signals, we can figure out what the total angle is. We also have, so these 8 thermistors, which by the way cost about 10 cents each, so they're really cheap, little surface mount devices. These 8 really are required for the operation. The 9th is connected with a fixed resistor. What we actually did is glued this to the heating resistor to get a measure of just the temperature of the board. That turns out to be useful because of the thermal effects that we'll talk about, that we'll see. But we, like I mentioned at the start, this is actually an idea that we got from a CMOS transducer. So originally, it's been demonstrated quite a few times in CMOS where they have a center heater and then on chip thermistors surrounding it. And you're talking about maybe like a 2 millimeter by 2 millimeter die. So something really small. And what we're trying to do is make what in CMOS terms is a huge version of this. And we wanted to we're basically trying to figure out, could you do this with discrete surface mount components? Because that's the way to make it really cheap. It's just a really small printed circuit board with 9 or 11, depending on how you configure it, surface mount components. Very easy to do, but would the distances work out? Would the sizes work out? So in order to do this, we kind of experimented with how we laid out the board. So there are 4 different versions here, just showing the top and bottom copper layers. The thermistors are these on the outside. And then the heating resistor, we experimented basically with aligning it with one of the quadrants, putting at an angle, because if you look at the data sheet for these resistors, and you look at the thermal pattern they show, it's sort of an oblong shape around that device. So we're curious about how the slight asymmetry of the resistor would show up. It should show up as an offset in the angle behavior. And then the other thing we thought was, well, maybe if we put the heating resistor on one side and we put the thermistors on the other side and sort of heat through the board, and maybe that would have an effect on the behavior. Okay, so So these are the 4 prototypes that we built. And we did really basic tests with all 4 of them. And we ended up using this one with all components on the same side. And the angled resistor, although the difference between the angled resistor and the straight resistor were sort of negligible. So that's the sort of layout. Here's a photograph of the board that we used. And the key thing that we discovered that was sort of a surprise to us was that we ended up having to mount it so that, sort of upside down, so that when it's mounted on the on its base, the components are on the underside. If we expose this face to the wind, we get a lot of turbulence on the surface, and the measurements were far noisier than if we flipped it over. So we actually populate the board and then put it face down onto this mount so that the sensor doesn't disturb the airflow over the surface. So I actually brought just the board with me, and I'll just pass it around so you can get a sense for how small and lightweight, which is also important for our boats, the sensors. The funny kind of mounting is it's a styrofoam ball. The idea is for the wind to kind of flow over the face even when it's heeling. So with that device, it's really cutting it off here. We built a wind tunnel. Actually, you can see the wind tunnel on the previous slide. It's just a fan, and then we used drinking straws to get a nice airflow. In that wind tunnel, we just rotate the sensor with respect to the wind to a variety of different points, and we measure those bridge voltages, and then calculate, based on their relative size, we calculate the angle. These plots on the right show, for 2 different wind speeds, the measured angle. So the x-axis here is the actual angle, y-axis is the measurement. You can see it's not a perfectly straight line, but it's pretty repeatable over different wind speeds, which is important. The sort of nonlinearities can be corrected for using a lookup table. And if we look at the raw data, these black curves are at the high wind speed. The red curves are lower wind speeds. You could potentially use this as an anemometer as well, in the sense that you get more signal for faster wind speed. So these 2 power levels, the 100 milliwatts and the 500 milliwatts, we chose these, so it's a 500 milliwatt rated resistor, so that's the maximum power we can use. And then the 100 milliwatts is the same power level that the Austria Microsystems chip requires. So this is sort of a direct comparison to running the magnetic encoder. Unfortunately, it's somewhat cut off, but these gray bars, which indicate the noise, are slightly larger for the low power, but it would still be usable at 100 milliwatts. The main issue we ran into, though, was this temperature drift, where because the devices are not perfectly matched, and actually their values vary differently with temperature, they don't track very well. If we heat all of them equally, so no wind, just heating the device, we see a bridge voltage that actually changes with temperature. This is the drive voltage. And this creates an offset, and you need to calibrate this out. And in the CMOS versions, they actually run into the same problem and characterize this and calibrate it out, which seems to be sort of a straightforward operation. But we haven't really done this enough in the field to know how reliable and how consistent that calibration will be. The other sort of interesting thing, and probably something that comes to mind when you think of using a temperature signal in a control loop, is that we know that thermal time constants tend to be really slow. And in fact, we saw this with the thermal wind sensor, and that the step response for the configuration I showed, where the components were mounted on the underside of the board, was very slow. So for this experiment, what we did is we had the wind on, and the sensor in one position, and then we basically step rotate it, just manually rotate it to a new position, and measure the angle over that time and see how long it takes to settle. And in the configuration I showed earlier, it takes about 6 seconds to rise. I do RF, so everything's nanoseconds. But it takes 6 seconds, actual seconds, to settle, which is really slow. A fast boat would not be able to operate a controller with that much delay. The thing that's causing this issue is that we have a really thick printed circuit board, and the heat conduction through that board leads to a very slow thermal time constant. So if we had a thinner board, that would be dramatically improved. And we verified that by flipping it over, putting the components on top, where the measurement's not as accurate, but there's no thick insulator between the heater and the fluid, the wind blowing over it. And there we see about a 1 second rise time, which would definitely be fast enough for a lot of control systems. We heard earlier that the Micromagics, like, you want to kind of servo the rudder every 2 seconds or so. So a low pass filter that had sort of a 1 second rise time would be enough. Obviously, and for us, the idea would be to coat the surface of the components to give that really thin conformal layer that didn't introduce turbulence, and that would have the added benefit of waterproofing it, which is another good thing. So it's definitely a solvable problem, just not one that we have played with yet. The last consideration that we have is, because we're putting this on a boat, how does it respond to heel angle? Our wind vane sensors, we try to balance them so that even when it heels, it doesn't just flop over due to gravity. We sort of have a similar issue with the thermal thing. We just want to make sure that our measure of incident wind angle doesn't depend on how heeled it is, or at least doesn't strongly depend on that. And that was the idea with this spherical base. So the wind kind of comes in, and then nicely, we have some nice laminar flow over the face, and don't have any problem, aren't shadowing the wind with the sensor. And that actually worked pretty well. So what we did is fix the angle of the sensor with respect to the wind, and then sort of manually heeled it. And for a variety of heel angles, which is the x-axis here, we measured the wind angle. And it stays within about 5 degrees, which is actually our kind of measurement noise anyways, even when sort of standing up statically. And we did that over a range of about 0 to 40 degrees heel angle. We didn't go, I guess seeing the Micromagics out there, which are sometimes flat on their side, I don't know if this would still work, but I'm also not sure if you need a valid wind measurement when you're heeled over that much anyways. So in summary, it's very promising. We haven't done any field tests yet, so we can't really speak to how reliable or how much these temperature effects and time constants and stuff will, from a sort of complexity of calibrating this out, how much that will really affect us in the end. But it's very lightweight, cheap, and has no moving parts, which is just fantastic for this application. And but yeah, we certainly have some work to do with the coding and the calibration work. So maybe next year you'll see us. Our plan is to take the vane and this sensor run them both at the top of the mast and make sure that they agree before letting it loose with just the one. So certainly it's a redundant system, which would be very well suited for us. And any questions?
First of all, I have to say, very impressive for a hobbyist. Second thing is, I've got $20, I'll take 2. His third comment would be, but a few years ago somebody said there would only be a market for 6 computers in the world, but for a non-moving parts wind sensor, I would say there's only a few million sailboats that would like to have those. So, yeah, quickly patent it and market it.
Yeah, right.
Questions? Mark?
There's more of a comment, is that your problem about latency, if you have a 6-second latency, if you know it's a 6-second latency, then your control system doesn't really care, because as long as you know what your heading was 6 seconds ago, you can deduce the wind angle. Okay, it's averaging over a long period, but you know, because that's the problem with small boats, isn't it? They're changing heading all the time. But if you're integrating over 6 seconds effectively, you've got I mean, it's not going to be pure latency, is it? You're going to have some integration of wind directions over that 6-second period. But if you know what your heading was during that 6-second period, you should be able to do a fairly decent instantaneous snapshot. It just happens to be 6 seconds old. But for wind direction for a sailing boat, that's actually not that big a deal, because the wind direction, you don't attempt to sail on a 6-second wind shift basis.
For the micrometrics, it's much too long.
But provided you have the compass combined.
I disagree though, because if the wind direction doesn't shift by 90 degrees in 6 seconds, and if it does, actually your control system's probably going to be stuck anyway.
Our control loop time, the frequency of our loop crossover is it's much faster.
Yeah, fine. And I'm not disagreeing that you need to do it at 5 Hertz, but if the wind direction has changed by a significant, like 90 degrees in 6 seconds, you're probably in some pretty dodgy situations for sailing anyway. Because resetting your boat, trying to sail at that frequency, you're going to be using so much power and applying so much rudder and pulling sails in and out so much that you're going to stall anyway. So I think, when we're looking at wind directions for sailing, even somewhere like this, I mean, this is quite benign here, but even on some of the sheltered lakes, wind shifts over 30 seconds are the things you're interested in, maybe, or over a minute or two, not over 5 seconds. And as a human sailor in a dinghy, you might, think about cheating in and out on a few seconds basis. But I don't know, I just think that for most of what we're trying to do, 6 seconds is fine.
I agree, that's exactly what we do by software.
Yeah.
To make an average over the last few seconds.
But your boat is
Yeah,
really
of
is huge, right? I mean,
But
for the
as a small
micrometrics.
boat, if you consider a market of several 100,000, and
The size of your
the
boat.
most of them are
The size of your boat doesn't affect how.
As a moderator, I'm going to step out of being moderator and make a comment.
Well,
I would think that in the case where you're sailing off the wind and you're just simply trimming, there's no question 6 seconds acceptable delay. But if you're in like we saw in the last couple of days out here, and you're sailing in apparent wind down of a close haul to a close-winded boat, if you're suddenly luffing, pinching, 6 seconds is much too long because you'll stop. And so I think it is very much boat size and location.
6 seconds is to get to your final reading as well, isn't it? It's not, it's not like you haven't got a hint of what's going on. I don't know.
You're putting in a pole in a system that is at a really low frequency and getting like a huge amount of phase. I mean, speaking from like a control perspective, you're putting in a huge amount of phase shift. You're assuming that you're going to end up with a stable system.
But that's the point, isn't it? That you don't have to necessarily believe the wind reading you have now. You know what the wind reading was 6 seconds ago.
So you want to model it and then do like a feed forward.
Well, yeah, I mean, there's all sorts of things you could do looking at the slope, how it's changing. I mean, there's a whole ton of ways you can get around that in software without doing really horrible engineering.
And you can start responding.
Lovely.
initially.
Yeah, you could begin responding already, and then you can create what you think is likely to happen.
Yeah, no, it's true. I just, Alex's student earlier was talking about 2 second ruddering time as being the slow version.
Yes.
And that's,
I like your other solution for turning it the other way up.
Well, yeah, we can make it better. So,
Make it better.
yeah, make it better, and then the 1 second is.
If you want to mass
We
market,
don't add it. It doesn't add anything to the complexity or the power cost or anything to make it better in this case.
if you want to sell them to people with 60-foot sailboats, then 6
There we go.
seconds.
Yes. They can probably afford it too.
Don't mind paying
And you can fund an awful lot of Sailboat hobby by selling
But they will buy the $800.
They wouldn't be $10, $300.
Oh yeah.
I have one question. We had an ultrasonic wind system before, and one of the things we noticed was that over time, with the salt spray building up on the surfaces, we lost significant resolution. Would that happen in this case, or would you lose?
If it built up uniformly, and then it would probably just slow it down. Slow down this time constant by sort of thickening that layer through which would sort of heat conduction is the primary mechanism. Assuming you could coat everything in some protective epoxy or something, I think it would probably hold up to that pretty well.
Any other questions?
Just a comment on the first table you're showing the comparison between the different technologies.
Yeah.
One thing is really important, especially for tiny boats, is the power consumption, which you should also.
I didn't put that on there, yeah, that's
Right,
true.
because it's really important. For example, you look at that and you should buy if you have the money, ultrasonic. But even if you have the money, ultrasonic will, as far as I know, will take you 2 to 3 watts, something like that. And for some of these,
Oh yeah.
you get something like that, right? So everybody's using more or less the same, the AMR or something. And for for our own boat, that's the total power that we have.
Yeah, to be honest, we never really even considered doing an ultrasonic approach.
From the naval architect point of view, I'd like to see a column that says weight.
Yeah, I sort of lumped that in here,
Yeah.
but
What do you think is the effect of raindrops?
we tested that by putting a drop of water on it. It
Will depend on the tropics, I guess.
It cools, it basically, the problem was we couldn't de-embed, we hadn't de-embedded this offset variation with temperature, and so we had cold water, and so we put it on it, and immediately the response, like it would jump to some new thing and then settle out. I don't think it would actually do any, I mean, it would, again, probably slow down the transient behavior if you're either measuring the temperature and calibrating it out, or doing a thermal controller to drive the board to constant temperature. It could certainly recover from it. Yeah. But yeah, that's definitely a real issue with the boat application.
Great. And whoever put the sample in their pocket, hoping to take it away, make sure you return it to Taylor. I think we're going to hold more. This is a great discussion, but we do need to keep rolling along. And so, Mariano,
Okay.
you're good? Thank you so much, Taylor.
News about the bottom fish of the slide.